Good afternoon and welcome to Carlum Cymru sessions. This session will focus on Physics Year 13 Orbits and will be presented by Mr. Ridd from Cynvig School in Bridgend. The session will last around 45 minutes where the teacher will go through the relevant subject content. If you have any questions, please use the question and answer section and we will endeavour to answer your question during the session. The session will be recorded and the recording with any relevance resources uploaded onto the e-sgol website in the Carlum Cymru area. And without much further ado, may I introduce Mr. Ridd.
Thank you very much, Mrs. Owen. Sorry, that was my phone. Brilliant. Yeah, welcome to this little session now on orbits and the wider universe. So this is one of the later topics in your Unit 4 course. There's a lot to get through here. I would recommend, if you're watching this for the first time, to go back and have a look at gravitational fields from a previous video. A lot of those equations are very helpful and inform a lot of what we're going to be learning about today. So, here is the specification, as I'm sure you have got a copy of. It's quite a lengthy topic, and we're going to start off with this bit here, Kepler's laws, and probably a little bit of Newton's laws of gravitation, and down as far as how Kepler's third law can be used in conjunction with Newton's law of gravitation to derive it. So, to begin with, I think it would be remiss of me not to mention a few important people. Nicholas Copernicus, you might have heard the name Copernicus before. I don't know, maybe you have, maybe you haven't. But he was the first to really put forward the heliocentric model of the solar system. Up until that point, the solar system was regarded to be geocentric, i.e. with the Earth at the centre, with all the planets orbiting and the sun including that orbiting around the Earth. This became very problematic. The more astronomers started to study the heavens, as they were called then, or the skies, the more they realized that there were major issues with this model. And Copernicus, his genius wasn't appreciated in his lifetime, and sadly he went to his death not being vindicated, which is a good word to use, I suppose, for his understanding of the solar system. And it wasn't until some 50 or so years later that some other people contributed that the theory was widely accepted. Of course, you know, the idea of the sun being at the center of the universe, if you like, at the time, or the solar system, was controversial for these reasons. You'd feel it, the Earth cannot be in motion, because were it to be in motion, we'd know about it, right? You'd feel that motion beneath your feet. And it was also said that the positions of the stars would have moved as well. So sadly, it wasn't until people like Tycho Brahe, Galileo with his invention of the telescope in 1609, and Johannes Kepler for his mathematical genius, it wasn't until those people made their contributions that we actually got to a point where the heliocentric model became accepted. So Kepler then, skipping straight to him, he came up with 3 laws which you need to be aware of for your A-level. The first one, very simple law here, and that is that orbits aren't necessarily circular. They can be, but they're more likely and more often than not are elliptical, with the sun at the focus. And the focus means it's sort of like the point at which the ellipse orbits about, really. The second law is a one which I haven't seen assessed, but we are going to pay attention to, and that is that an equal area will be swept out in equal time intervals. So this area here, right, if I call this A1, would be equal to this area here, A2. So in an equal amount of time, an orbit will sweep out an equal amount of area. And then finally, the third law, which needs probably a little bit more fleshing out, and one is more important in many respects for your course is the fact that the cube of the radius of the orbit, okay, which we'll say is maybe the average radius of the orbit, is proportional to t squared. Okay, so with that in mind, then we'll move on. Sorry, everyone. Apologies. A slight technical issue here. Very good. Okay. So one of the reasons why he came up with this idea was to do with the fact that when we plotted the radius of the orbit and the period of the orbit, we found that these sort of obeyed a straight line relationship. Okay, and from that, then we'll just jump straight into an exam question. All right, it says that Newton's third law can be derived from Newton's gravitational law, and the equation for centripetal motion show that for any object in circular orbit about the Earth, t squared is equal to 4 pi squared over gme r cubed, where t equals the period of orbit, r equals the radius of orbit, and g is the gravitational constant. Okay, so what we're going to do here now is start off by looking at Newton's, first of all, formula for gravitation, gm1 m2 over r squared. And we're going to compare this as well with his centripetal force equation, which is mv squared over r. Now, if we put these two equations equal to each other, which we can do, because if we imagine an orbit or planet in an orbit around the sun, then its force due to gravity and the centripetal force, and we can move in a circular path, must be equal. They must be the same. Now, we're going to say that if the sun was, let's say m1, let's say my little planet is m2, then we're going to call m1 the mass of the sun, the little planet m2, and these m2s will then cancel. If they cancel, we can also cancel down here with the r's. What we are left with is that v squared, sorry, that's a v, v squared is equal to g m over r, right? Now, from that, we need to just do a little bit more work, because we're getting close to the equation, but we're not quite there. Now, the velocity of an object moving in a circular path is going to be given by 2 pi r, which is the circumference of the circle, over t. So v squared is going to be 4 pi squared r squared all over t squared. And what I'm going to do now is I'm going to substitute this v squared into our original equation, so that we end up with 4 pi squared r squared over t squared is equal to g m1 over r. All right. And now I'm going to tidy this up, and we're going to say that r cubed, and take that r up, this r goes up here, becomes r cubed, and that is equal to gm over 4 pi squared times t squared if I take the t up the other side. So we are left with this equation. All right. Now, as it turns out, I haven't done it in exactly the same form. It is the same thing, except the constant, the gm over 4 pi squared, is on the other side, so it's inverted, but it's essentially the same thing. Now, incredibly, not only did this piece of mathematics, which Newton used to derive this relationship, because if you look here, we have managed to prove that r cubed is proportional to t squared. We've proven it mathematically, but if you think about what Kepler had done empirically in showing this relationship, what Newton had done is he confirmed it mathematically. So that's a really good example of experimental observation and theory sort of meeting together, which is something we really like in physics. But at the same time, what's incredible here is if you look at this gradient here, right, this gradient is going to be given by this here. And that gradient is going to tell you the mass of the sun. So not a bad day's work. Newton, in sort of confirming that with theory, managed to actually put together a pretty decent estimate for the mass of the sun at the same time. Not a bad day's work, I think you'll agree. So we're going to use Kepler's laws now to do this next question. It says the radius of the geostationary orbit above the Earth's equator is 42,000 kilometers, and the Earth-Moon distance is 380,000 kilometers. Use Kepler's third law to calculate the period of the Moon's orbit. Right then. So the important thing to remember here is that if r cubed is proportional to t squared, then that also means that r cubed over t squared is equal to a constant. So what we're going to do then is work out, in the case of the geostationary orbit, we're going to work out what that constant is. So we're told that the orbit is 42,000 kilometers. I'm going to change that to standard form. So it's 4.2 times 10 to the 7 cubed divided by the time. Now you might be thinking, well, we haven't been given the time. And it's a really sneaky, evil question in a sense, because you have been given the time. And it's almost pulling on a piece of knowledge that you need from key stage 4 here as to what a geostationary satellite is. Geostationary meaning stationary with respect to Earth, therefore orbiting in the same time as the Earth takes to complete one of its rotations. So the geostationary time, if you like, this geostationary bit means 24 hours, right? That's what t is. So we're going to change that into seconds. We're going to say 24 times 60 times 60. And we're going to remember to square all that. If we do that, we end up with 9.9 times 10 to the 12. You can check my math if you like. But what that means is this is for the satellite. So maybe I'll put a little subscript here for satellite. But that would also mean then that for the Moon, this relationship would also have to equal the same constant. Excuse me. So that equals 9.9 times 10 to the 12. And now we can start putting in our other numbers, because we also know that that's equal to 380,000 times 10 to the 3. Not the most elegant standard form here. That's cubed. Divided by t squared. Now we don't know what the time period is. That's what we're after. And then if you rearrange that, you end up with a value for t equal to 2.35 times 10 to the 6, which might not mean much because it's in seconds. So we can go one step further then and then convert that into days, and we end up with 27.2 days, which is consistent with how long a lunar orbit is. If you think about a lunar month, it's about that long. Right, now part C, it says, estimate the minimum possible orbital period for a satellite orbiting the Earth, stating any assumption that you make. The radius of the Earth is 6,370 kilometers. So what is the minimum possible orbital period? Well, that would happen at the minimum possible height. The minimum possible height. Now, we'd have to sort of make some kind of assumption here. Like, maybe you can all think of that what assumption is. We know that the radius of the Earth is 6,370. We couldn't have a satellite orbiting at that distance because that would mean it was whizzing round through the Earth's atmosphere just above our heads. So that doesn't really work. So what we're going to do is maybe add 100 kilometers. Let's just do that. Because we're pretty much in space at 100 kilometers, right? And then we're going to say that R is equal to 6,470 kilometers. Then we're going to do our R cubed over T squared. If we remember, we worked that out to be 9.9 times 10 to the 12. And then we're going to rearrange this so that we've got T is equal to the square root of 6.47 times 10 to the 6, which is my radius in meters, and that's all cubed, divided by 9.9 times 10 to the 12, and then what we end up with is 5,230 seconds. But no one really ever says that. It's got 1.45 hours. Now, the International Space Station, as it happens, has a very low orbit, and consequently, I think it orbits in around about a time of 90 minutes. So they see, many sunrises during a day. So that would be an example of a satellite in what we call a low polar orbit. So we're going to say Kepler's 3 laws of planetary motion done. Newton's law of gravitation in simple examples include the motion of planets and satellites. We've used that. How to derive Kepler's 3rd law, did that. And we're going to move on to this next bit now. So how to use data on orbital motion, such as period of orbital speed, to calculate the mass of central object. We're also going to look at how the orbital speeds of objects in spiral galaxies implies the existence of dark matter, and how the recently discovered Higgs boson may be related to dark matter. So we've got a bit to cover there. Right, so we're going to jump in straight into the dark matter part, and we'll talk about how orbital velocities are related to the mass of the object holding that object in gravitational field. So here, this is a typical galaxy. We've got a central galactic bulge. This would be quite similar, not too dissimilar to how the Milky Way would look end on. So in the center, we've got most of the mass of the galaxy, but then it sort of tapers off as we get towards the outside, okay? So less and less mass toward the outside. Now, this is important because, excuse me, let me just move on. Scientists and physicists, cosmologists have studied the rotational velocities of these stars. Now, it won't be a surprise to you, and you should already know, that the planets, if you like, at the outer reaches of our solar system, a planet like Neptune, is traveling far slower than a planet like Mercury. So the further it's out, I mean, we've already sort of expressed it when we said that R cubed is proportional to T squared. If we are far away, the bigger R is, all right, the longer the time period will be, and therefore the slower the velocity will be. So that stands to reason. We can sort of, though, derive an equation to help us with this, and we've already pretty much used this equation, or we came very close to it. If I, again, take Newton's laws of gravity and centripetal force, we can do Gmm over R squared. We put that equal to mv squared over R. We cancel, and we cancel the little m's. Now, in this case, the little m's, if we're talking about a galaxy, the little m here that we're going to be thinking about is a star, which is right on the outer reaches of the galaxy, right far out, right past the edge. right, at the very edge of the galaxy, away from most of the galactic mass then. So if you think of a little star out there, we'll cancel that mass, right, in that equation. And then this m here, I should mention, this is the mass of the galaxy. If we then take one step further and we rearrange this, we end up with V is equal to the square root of Gm over R. So V, sorry, let me just laser pointer, awesome there today. Gm over R, all right. So with this equation, we can make really sound predictions as to what theoretically the velocity of such a star at the edge of a galaxy would be. And if we were to do so, as soon as we get away from the main mass of the galaxy here, it starts to taper off, right? And essentially what starts to happen is V really is proportional to 1 over R, the square root of R, right? And we should see it tail off nicely, and we should see that orbital velocity come right down. However, and this is the important bit here, when we look at the actual observations of these stars at the edge of galaxies, we find that observation, this is obs, tells a very different story. There's something going on here. Now, what is that? Well, it's important to mention as well that this velocity here, as we said, that m is the mass of the galaxy. How do we measure the mass of the galaxy? Well, one way to do it would be to think of the total luminosity of the galaxy. So one way you might do it is look at the total luminosity. And from the total luminosity, you can make a judgment as to roughly how many stars there are. So you'd have a fair idea of what the mass is of a typical star. Then you'd have an idea then of the total mass of that galaxy. So from that then, what we're able to do, as I say, is make that prediction. So what would appear to be the case then with this observation is that there is far more mass in the galaxy. And we say that because if you like the V, all right, that is predicted is far less, right, that's less, sorry, far less than V measured. Okay. So what is responsible for this extra mass? Well, the extra mass, which is causing this, if you like, greater gravitational pull, which is causing this higher velocity, we call dark matter. Why do we call it dark matter? Well, one answer would be that we don't know a huge amount about it. We know that it's not interacting with light in any way. So we know that the light from the galaxy is passing through this invisible matter that we can't see. Yet we know that, in fact, most of the mass of this galaxy is, in fact, dark matter. So these stars are going around way, way, way too fast for our theory to make sense. And the only way that the mathematics can make sense is if this mass here is far, far larger than what we are estimating it to be. And that's where we have sort of said, well, it must be dark matter. Now, that's not the only piece of evidence, and I was very keen to show you this image. Here you can see another very strong and compelling piece of evidence for the existence of dark matter. You can see, I hope, here, see this like smudging. These are galaxies. They might even be the same galaxy. And this smudging is caused by light being distorted as it passes through a very strong gravitational field. And that gravitational field is being created by some form of matter which is completely non-interactive with light. So we know there's a huge amount of mass in between us and these distant galaxies, yet it is completely transparent. It doesn't interact with light at all. It's not blocking the view in any way, shape or form. So there is this distortion caused in space. And again, we don't really know what's causing it. This is a nice little graphic as well, showing that the light from this galaxy here could and does and has arrived at Earth via two different paths. Look. So because of the bending of space, because of the distortion caused by the dark matter, we have managed to see the same image or the same galaxy twice, two different ways. Right then. So how is dark matter linked to the Higgs boson? So in 2012, the Higgs was discovered. In history books, hundreds of years from now, you will have lived through a time that will be talked about for a long time yet, because in history books, hundreds of years from now, 2012 will go down as date that the one of the last, I'll say one of the last just in case, subatomic particles were discovered, the Higgs, and it was a pretty big deal because it completed our picture of the standard model to an extent. A few caveats there, but that's a whole other lecture. So the Higgs boson is a very, very massive particle, and it decays very, very quickly. It was discovered at the LHC in CERN in a particle accelerator, which you've probably done a little bit of in year 12. And the energies are so large they're able to, recreate conditions that were present at the beginning of the universe at the Big Bang, and discover this particle from which other particles are created. This is one of the reasons why it's called the God particle. It's nicknamed the God particle because from this we have these two decaying muons here. You can see these are decaying muons, and that muon decay goes on to create quarks and other leptons. So that's the reason why it's called the God particle. Now, the reason why it's in the syllabus here is because it is theoretically possible then that the Higgs not only creates the regular matter that you come across in the standard model in year 12 and even a little bit in year 13, but also that it creates the dark matter as well. Now, as to what that dark matter looks like, what its characteristics are, we will endeavour to find that out. And at the moment at CERN, they are turning up the energy on the LHC. They are trying to find evidence of dark matter using the particle accelerator. Now, I'll be honest, in terms of the specification, it's very, very vague as to what you will be asked about with regards to the Higgs boson. And in fact, in your revision guide and online, it's even more vague. So what I will say is this: be aware that the Higgs boson is a very large subatomic particle that decays very quickly into all other forms of matter, essentially, and that it could, in theory, also be the mechanism by which dark matter is created. But there we are. Okay, so binary star systems and exoplanets. I'm not going to go through the theory or derive any of these because we don't need to. We're going to save the time. But with binary planets, binary star systems, we have to appreciate that they will orbit around a common central mass. Now, if we have a situation like where the sun is far, far, far more massive than the planets orbiting it, or if you have a star that's far more massive than the planets orbiting it, then it won't move very much. But I mean, just think of this scenario for a second. Let's draw it up here. What if, you had two masses which are absolutely equal. If they were absolutely equal in size, then of course you'd expect these two objects to orbit about a common centre of mass, which would be in the equidistant between the two. If, of course, we started to mess around with this then, and we had one which was a little bit bigger than the other, then we might find that, or might expect that this mass was shifted a little bit, or the centre of mass was shifted a little bit more towards the larger object, and they would both orbit around that common centre of mass. There's a nice diagram that illustrates it here. So here we've got M1 on its merry orbit around the centre of mass, which is here, that dot, and we've got M2 on its merry orbit. Now, there's a couple of things that we need to bear in mind when we think about problems involving binary star systems or stars with large exoplanets. So we're really talking about situations where the masses are comparable, or if you like, M1 is not much bigger than M2. These stars, or if you like, the star and the exoplanet, will have the same orbital period. That's important. We're going to need to use that in some questions, I'm sure. Also, for some questions, when you're using these equations, some questions, M1 will be far greater than M2. All right. And if M1 is far greater than M2, then we can make an assumption. We can then say that M1 plus M2 is pretty much the same as, the mass of M1. So if M1 is far, far bigger than M2, we kind of just say, well, it's like negligible mass, all right? It's like, oh, you know, what's the mass of you plus your toenails? It's pretty much the same as the mass of you, isn't it? Your toenails don't make much difference, I guess. I don't know. You might have huge toenails. Yeah. So we've got another formula down here as well for time period. And we're not going to derive this, but we've got the time period for two objects orbiting each other given by this formula here, where d is the distance between the objects. Yeah, so let's move on. Another important bit of physics you're going to need for the next set of questions is going to be to do with the Doppler effect. Now, the Doppler effect is the apparent change in wavelength due to an object moving towards or away from us, and in particular, a wave source moving towards or away from us. So if we have a light source moving away from us, it causes a change in the wavelength, and in particular, an increase in the wavelength of light that it's producing. This would be the velocity, or I should maybe say the relative velocity. Einstein would prefer that. And then finally, this is the speed of light. And this here is, I guess, the original wavelength, or the correct wavelength. A better term than that. I did have a little example here. I don't think we'll do it now because I'm conscious of time, and we're going to push on and do a little bit more. So we will be using this equation. It is a relatively straightforward equation. So like I said, when a wave source moves relative to an observer, there will be a change in the wavelength depending on whether it's moving towards us or away from us. We can use this change to measure the velocity of that object. Right, let's try another question then. So we got a star and a planet orbit their mutual center of mass as shown in the diagram. This is not to scale. So we've got here a large mass. Why don't I label this up? M1, M2. That's helpful. And while we're at it, I'm going to label this as R1, the distance from M1, and I'll label this up as, you guessed it, X. No, R2. What am I missing? R2. Calculate the period of the orbit. Well, this is nice. We can just use our big old formula and pop our numbers in. Now, on top here, we've got D, which is 5.2, the distance between the two, times 10 to the 9, and that's all cubed. And we're dividing that by 6.67 times 10. Hang on. It's not 6.67. Mr. Ridge just had a little bit of a G, isn't it? The gravitational constant is times 10 to the minus 11. Oh gosh, right. We'll say G for now, right? The gravitational constant times 6.2 times 10 to the 22. It's because I'm using Planck's constant today. That's what it is. That's what's happened. And anyway, if you put that all together, you end up with 1.16 times 10 to the 6 seconds. All right. Calculate the distance of the center of mass from the center of the star. Well, to do this one, we'll use R1 is equal to M2 over M1 plus M2 times D. Now, you pop all those numbers in, we end up with 2 times 10 to the 27 times 5.2 times 10 to the 9 all over M1 plus M2, which again is 6.2 times 10 to the 28, sorry. 28. That should have been 28. My bad. 28. And that then comes to 1.7 times 10 to the 8. All right. And that's distance, so that's meters. Right. Moving on. See if we can practice as much as we can. We've got another 7 minutes, so we'll try and use it up to do as many of these questions as possible. So the center of mass of this star planet system is at rest relative to Earth, and the system is viewed edge on. When analyzing light of wavelength 656.3 nanometers from the star, astronomers measure a maximum redshift of 2 picometers. Determine whether this shift is approximately consistent with your answers to AI and II. Right. So a couple of things to do here. First of all, we're going to start off by working out the velocity. The velocity, we'll say, is, well, distance over time, or in this case, 2 pi r over t. And we'll say 2 pi times 1.7 times 10 to the 0.7 times 10 to the 8 divided by 1.16 times 10 to the 6. So these are our answers from the previous parts of the questions. These are answers from the previous bit. All right. Sorry. Let me go back there. Oops. All right. Oh God. Gremlins are in today. And that comes to 910 meters per second. And now we want to sort of confirm that. So this is what it's saying. Determine whether this shift is consistent. So let's then try and work out using the Doppler effect whether this is confirmed. So remembering that the Doppler effect is delta lambda over lambda is equal to V over C. And then we can say that V is equal to delta lambda times c over lambda. And if we put all that in, and remember that we're talking here now of a very small shift, we can pop that in. We end up with a speed of 914 meters per second. So, you know, does that confirm? Is it consistent? Yeah, it is consistent. All right, consistent it is. Oh, by the way, that there is our delta lambda. So consistent. It's similar, isn't it? All right. In 2008, a large planet was discovered orbiting a large star using the following data obtained from the spectral observation of the large star. The graph shows the large star's radial velocity versus time. Here, radial velocity is the component of the star's velocity towards the Earth. Right. So we've got a graph, we've got a fair bit of information here, and we've got the radial velocity, probably determined using the Doppler effect. So when the star was moving towards us, the light would have been blue shifted, if you like, the wavelength would have been ever so slightly shorter, and from that we would have been able to work out its radial velocity. With use of the diagram, explain why this variation in radial velocity occurs. Right, so this is a tricky one here. We're gonna have to use a diagram. So I'm gonna draw maybe my star, and that is orbiting about the center of mass. And as it's orbiting about the center of mass, there would be was it two stars? I can't remember. No, a large planet. The large planet would be sort of orbiting around in this direction. And if we were looking at this, then if we were looking at this from Earth, say, yeah, if we're looking at it from Earth, and let's say Earth was over here, all right, Earth was over here, then that would mean that we could say that in position shown, in the position shown, star is moving away from Earth as it orbits around center of mass. Being lazy, right? I'm just writing com. All right. So that would be a diagram. Maybe we'll put down a star. We'll label it up a little bit. This would be planet. That would do nicely. Show that the radius of the orbit of the large star is approximately 4 times 10 to the 9. Right. So with this one, we'll do V is equal to 2 pi r over t again. V is equal to 2 pi r over t again. And r is equal to v times t all over 2 pi. Right. So from that, then we just plug the numbers in. That's equal to. Now, where we're going to get these numbers from? Well, we're going to get them from the graph. Okay. So why did that go back? We go back here. Our graph here, you can see that the highest radial velocity here is at this point, which is about 1700. So we'll say r is 1700 times 170 times 24 times 3600. Now, why have I chosen those numbers? Because that is going to be the time, all right, just converting that into seconds, and then we divide that by 2 pi, and we end up with an answer which is equal to 3.97 times 10 to the 9, and that's meters, which is, of course, approximately 4 times 10 to the 9 meters. All right. just looking at the time now, that's 45 minutes. So I'm just going to briefly recap what we've gone through. All right. By showing you our specification. So we've done Kepler's 3 laws. We have also looked at how we derive Kepler's 3rd law, a very important one, that, using Newton's law of gravitation. How to use data on orbital motion, which we've just been doing now in the past with the questions that we've done. Calculate the mass of a central object, or in fact, distances. We've looked at how orbital speeds of objects in spiral galaxies implies the existence of dark matter. The notion that speed of those stars towards the outer part of a galaxy is far, far too high. Our theory is predicting a low value based on the mass that we are estimating, but what we're actually getting is a far, far higher velocity, and therefore our conclusion that we're drawing is that there must be some unaccounted mass that we are just not detecting, which we call dark matter. We also discussed briefly how the Higgs boson may be related to dark matter. In other words, the idea that the Higgs boson may be the particle, or maybe creating dark matter when it decays. How the position of the central mass of 2 spherically symmetric objects, given their masses and separation, and calculate their mutual orbital period in the case of circular orbits, and we've just done that as well. We did make ever so slight inroads into this next one here. We did the Doppler relationship. We got as far as this one here as well, to determine the star's radial velocity. But we didn't sadly get as far as Hubble. We didn't get as far as the great man himself. So maybe we'll have to save that for another time. Thank you, everyone.